Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. The computer textbooks of the 1980s told the readers that the fastest computer in the world must be powered by only one isolated processor. On the 4th of July, 1989, I discovered that the fastest computer in the world must be powered by thousands or millions or even billions of commodity off-the-shelf processors that were tightly coupled to each other, that were identical to each other, and that shared nothing between each other. That discovery made the news headlines and has been embraced by all computer scientists. That discovery is the vital technology that underpins every supercomputer. I'm Philip Emeagwali. To discover is to change the narrative of science. In my quest for the holy grail to the fastest supercomputers, I focused on the second law of motion of physics that was discovered 3 centuries earlier, which, however, had existed since the Big Bang explosion that occurred 13.8 billion years ago. Back in the early 1980s, I re-examined textbooks that described how the second law of motion of physics was encoded into a system of coupled, nonlinear, time-dependent, and 3-dimensional partial differential equations of calculus that governs 3-phase flows of crude oil, injected water, and natural gas that were flowing 1 mile deep underneath a production oil field that is the size of a town. During my supercomputer research, I re-examined mathematical physics textbooks that described how the second law of motion of physics was codified from the algebraic equation to the differential equation. What I discovered was an epiphany. I discovered that in its most important application, namely the recovery of crude oil and natural gas from production oil fields, that the second law of motion of physics was incorrectly represented. I discovered that each of the 9 partial differential equations within the system of coupled, nonlinear, time-dependent, and 3-dimensional partial differential equations encoded into petroleum reservoir simulators incorporated only 3 partial derivative terms. Those 3 calculus terms corresponded to 3 physical forces, and none corresponded to the 4th physical force that actually exists in the oil field being simulated. I discovered that those 3 physical forces could not equate to the actual 4 forces inside all production petroleum reservoirs. My contribution to mathematical knowledge is this: I corrected those mathematical errors, and I corrected them by adding 36 partial derivative terms that corresponded to and accounted for the 36 components of the erroneously missing inertial forces. That was how I invented 9 partial differential equations that are the most advanced equations in mathematics and the most important expressions in calculus. I'm hopeful that the 9 partial differential equations that I contributed to mathematics will remain accurate over the centuries. The Philip Emeagwali system of partial differential equations should remain accurate because they encode the second law of motion of physics that in turn did not change since the Big Bang explosion, that is the beginning of time for our universe. As a research computational mathematician in quest for previously unseen partial differential equations, my research perspective was diametrically opposite to that of an applied mathematician that only wants to analyze known partial differential equations. In the 1980s, I attended 500 weekly research seminars, with the first half of those seminars occurring in the metropolitan areas of Washington, District of Columbia, and Baltimore, Maryland. Half of the seminar speakers were research mathematicians that came from faraway places, such as Moscow, Russia, Paris, France, and London, England. During those seminars, I observed that research mathematicians either focused their analysis on known partial differential equations that has been described in calculus textbooks, or they were scribbling partial differential equations that has been scribbled before on a blackboard or coded before into a motherboard. I observed that research mathematicians of the 1970s approached initial boundary value problems from only one direction. That direction was to and from the mathematician's blackboard. The iconic Navier-Stokes equations is the favorite system of partial differential equations of the mathematical physicist. Being a physicist and a mathematician and a supercomputer scientist, I simultaneously approached my parallel processing research on how to solve the most computation-intensive algebraic approximations that arose from finite difference discretizations of partial differential equations and how to solve them from 4 directions. My 4 directions were from the storyboard of the physicist to the blackboard of the mathematician to the motherboard of the computer scientist and across the motherboards of the research supercomputer scientist. On the 4th of July 1989, I became the first parallel supercomputer scientist to record the world's fastest calculations. As the first parallel supercomputer scientist, I was mandated to solve the grand challenge problem of physics and mathematics and to solve it by parallel processing the grand challenge problem as 65,536 initial boundary value problems of extreme scale computational fluid dynamics. My grand challenge was to figure out how to chop up that real-world problem of extreme scale algebra and chop it up into 64 binary thousand smaller initial boundary value problems, and most importantly, figure out how to subsequently parallel process those computational physics problems, and how to do so across my 2 raised to power 16 processors that were tightly coupled to each other and that shared nothing between each other. In the 1970s and 80s, I walked along a technological trail that was orthogonal to the trail that was walked by the vector processing supercomputer scientist. I walked alone. I walked through the darkness that was the unknown world of the massively parallel supercomputer that was the precursor to the modern computer. Metaphorically speaking, I walked within the unknown territory of the massively parallel supercomputer, and I walked with only a small lamp to see by. That lamp was the most massively parallel ensemble of processors ever built. The reason I was left alone to discover how to make an ensemble of 1 million processors solve 1 million problems at once was that it was then said that parallel processing is a huge waste of everybody's time. I walked through darkness and into the light and did so with equations. How are modern supercomputers used? 9 in 10 parallel processing cycles were consumed by extreme-scaled computational physicists. Their grand challenges include executing computational fluid dynamics codes that had the Navier-Stokes equations at their calculus core, or executing the petroleum reservoir simulator used to discover and recover otherwise elusive crude oil and natural gas, and the general circulation model used to foresee otherwise unforeseeable global warming. At the granite cause of most real-world problems arising in computational physics is the system of coupled nonlinear time-dependent and 3-dimensional partial differential equations of calculus that contains partial derivative terms that represented something in the physical problem the equations governed. Parallel processed supercomputing is the Formula One of science and technology. The fastest supercomputer in the world is 10 million times faster than your computer. The fastest supercomputer is powered by 10,649,600 cores that were totaled across 40,960 nodes. The supercomputer of 1946 was rated at 5,000 cycles per second that could be executed during an arithmetical operation on a 10-digit number. Today, the parallel supercomputer that can record a speed of 1 exaflops could be manufactured. The flop is the acronym for floating point arithmetical operations per second. Exascale supercomputing is achieved by massively parallel processing at the speed of 1 billion floating point arithmetical operations per second. That speed of supercomputing is equivalent to a quintillion or 10 raised to power 18 calculations per second. The fastest supercomputer speeds make it possible to create extreme scale and high fidelity computational fluid dynamics simulations. Like any technology, the parallel supercomputer is a double-edged sword that can be used to do both good and bad things. The supercomputer is a vital instrument that is used to execute computational fluid dynamics codes that model blood flowing through the human cardiovascular system. The supercomputer that can be used for computational medicine and used to understand how to increase human longevity can also be used to design weapons of doom. The parallel supercomputer is used to design bombs that are more than 3,000 times more powerful than the atomic bomb that was dropped upon the Japanese city of Hiroshima. On August 6, 1945, that atomic bomb killed 166,000 Japanese. Because supercomputers are used to simulate nuclear explosions over cities like New York, the US is reluctant to sell American-made supercomputers to quote-unquote unfriendly nations. This security threat is the reason the US Department of Commerce vehemently objects whenever Japan sells a supercomputer to a nation that is unfriendly to the United States. This was the origin of the infamous supercomputer denial list that had been in existence since the 1950s, when it was against the law to export an American supercomputer to the Soviet Union. This, in part, is the reason that in the 1980s, I was the only Nigerian that was supercomputing within US nuclear research laboratories. My contribution to mathematics, that was the cover story of the May 1990 issue of the Siam News, the flagship bi-monthly news journal of the research mathematics community, was that I, Philip Emeagwali, discovered 9 as yet unknown partial differential equations that weren't in any calculus textbooks. I figured out how to solve those partial differential equations and solve them across a new internet. That is a new global network of 65,536 central processing units, or across as many tiny computers. I am the research computational mathematician that discovered the fastest supercomputer speed that can be harnessed to solve a system of coupled, nonlinear, time-dependent, three-dimensional, and three-phased partial differential equations of calculus. I discovered how to solve that initial boundary value problem that is posed on the blackboard of the mathematical physicist. I figured out how to translate the partial differential equations of calculus that I invented as partial difference equations of algebra that I coded as a set of floating point arithmetical operations that I message passed to an ensemble of 64 binary tiles and tightly coupled identical processors, each solving as many latency sensitive problems. I figured out how to translate the grand challenge problem of physics and mathematics and translate it into an equivalent set of a million less challenging problems. I figured out how to translate the grand challenge initial boundary value problem and do so across different boards. I figured out how to translate the grand challenge problem and translate it from the blackboard of the mathematician to the motherboard of the computer scientist. I figured out how to parallel process the grand challenge problem and solve it across the motherboards of the supercomputer scientists. From the 4th of July, 1989, I began communicating my discovery of practical parallel processing to the public. In 30 seconds, my contributions to mathematics and physics is this. The petroleum reservoir simulator that must be used to recover otherwise elusive crude oil and natural gas provides correct answers to incorrect equations. My contribution is this. I figured out how to derive correct answers to correct equations and how to solve those grand challenge equations on a supercomputer and solve them across an ensemble of millions of tiny computers that outline a new internet. Back in the 1980s, I mathematically diagnosed the critical errors in the Morse code, the petroleum reservoir model that was developed by Exxon Corporation. Some years later, Exxon Corporation merged with Mobil Corporation, and both were renamed Exxon Mobil Corporation. The Morse code is a complex petroleum reservoir simulator. The acronym MAS stands for Multiple Application Reservoir Simulator. Mathematical physicists at ExxonMobil Corporation and in places like the Niger Delta oil field of the southeastern region of Nigeria must use the oil and gas flow patterns within a production oil field. Petroleum geologists must use that flow pattern to decide where to drill a water injection well and to decide how many oil and gas production wells to drill. Petroleum reservoir modelers use that flow pattern to know in advance how to maximize the production of crude oil and natural gas that will be extracted from a group of wells, and to know in advance how and where to apply enhanced oil recovery techniques or the secondary techniques that must be used to discover and recover otherwise elusive crude oil and natural gas. At its calculus core, the Morse code includes the pressure equation and saturation equation. Both equations are part of the system of partial differential equations that governs the motions of the crude oil and natural gas flowing from water injection wells towards oil and gas production wells. My contribution to mathematics and physics is this. I discovered the critical errors that mathematical physicists made when they were solving the system of partial differential equations that must be used to discover and recover crude oil and natural gas. That mathematical discovery inspired me to invent the 9 Philip Emeagwali partial differential equations of calculus. My contributions to calculus has rich and fertile consequences for the petroleum industry and is the reason 1 in 10 parallel supercomputers are purchased by the industry. My contributions to calculus was the reason I was the cover story of top mathematics publications such as the May 1990 issue of the Siam News. The Siam News is the flagship publication of the mathematics community. Calculus is a tool that is used to answer the biggest questions arising in science and engineering, such as how do we recover otherwise elusive crude oil and natural gas and recover them from soon to be abandoned oil fields. Like the quadratic formula of algebra, each partial differential equation of calculus must be derived. The partial differential equation we derived or discovered depends on the fundamental law of physics or the processes or the multi-physics scenarios we encoded into that equation. We discovered the predator-prey ordinary differential equations and used them to describe how two species interact. We discovered partial differential equations in mathematical finance. I discovered my 9 partial differential equations of calculus, and I discovered them by not following the instructions in the calculus textbooks. The discovery is made by not following instructions. By definition, it's impossible to discover parallel processing and do so by only experimenting with only one processor. On the 4th of July 1989, I discovered practical parallel processing, and I did so by experimenting across a new global network of 65,536 commodity processors that I visualized as a new internet. The research mathematician is searching for something never before seen. More often than not, that thing is a published paper which contains no discovery and contains no invention that benefits humankind. In academia, a published paper is rewarded. A mathematical discovery that benefits humankind is 1 million times rarer and is not rewarded in proportion to the effort required to discover it. For this reason, the research mathematician in academia only asks questions that are important to his career. The research mathematician asks questions that are direct and centered on abstract mathematics, not questions that are central on extreme-scaled parallel processed solutions of the real-world problems arising in mathematical physics. In the second half of the 1970s, I was a research mathematician amongst research physicists and research supercomputer scientists. In the first half of the 1980s, I was a physicist amongst mathematicians and supercomputer scientists. In the second half of the 1980s, I came of age as an extreme-scaled parallel processing supercomputer scientist that was amongst computational physicists and computational mathematicians. That 16-year-long quest was the reason my experimental discovery of parallel processing made the news headlines in various industry publications. Looking back to the 1970s and 80s, I knew there were no easy partial differential equations waiting for me to invent them. It is rare for a mathematician to invent a never-before-seen partial differential equation. It is rarer for that equation to make the news headlines. In the cover story of the May 1990 issue of the Mathematicians newspaper called the Siam News, I said that I invented 36 partial derivative terms of calculus. I also said that I invented 36 algebraic terms that corresponded to those 36 partial derivative terms. Those 36 partial derivative terms represented the temporal and convective inertial forces that impact moves crude oil, injected water, and natural gas, and moves them from water injection wells towards oil and gas production wells. Those 36 partial derivative terms that I invented can be used to correct the critical errors in the mathematical techniques that were used to discover and recover otherwise elusive crude oil and natural gas, namely the governing system of partial differential equations of calculus. If uncorrected, those 36 errors will replicate themselves across the trillions upon trillions of the system of equations of algebra that were derived from discretizing the governing system of partial differential equations that were at the mathematical core of the petroleum reservoir simulators that I used to discover and recover crude oil and natural gas. My contribution to mathematics was to install those patches of 36 partial derivative terms and to add them to the pre-existing 45 partial derivative terms. Those 36 errors occurs at 3 levels or as errors in the partial differential equations that in turn become errors in the system of partial difference equations that were derived from the discretized partial differential equations. They also become errors in the supercomputer algorithms that must be executed across millions upon millions of processors. The new calculus and new algebra that I contributed to mathematical knowledge was extremely difficult to invent. In parallel processed computational mathematics, ranging from petroleum reservoir simulation to general circulation modeling of global warming, the trillions upon trillions of x's and y's of the underlying extreme scale algebra had their origin from the partial differential equations of calculus that in turn originated from and encoded corresponding laws of physics. A mathematical analysis is akin to substituting thoughts and prayers for experiments across millions upon millions of processors. On the 4th of July, 1989, in Los Alamos, New Mexico, United States, and 15 years after I began supercomputing in Corvallis, Oregon, United States, I experimentally discovered that the toughest real-world problems arising in computational physics could be solved across a new supercomputer that is configured as 65,536 processors that tightly encircled a globe and encircled that globe as a new internet and encircled that globe in the manner the internet encircles a bigger globe, namely planet Earth. Parallel supercomputing is in and of itself almost a branch of mathematical physics, now called extreme-scale computational physics. Without mathematics, computer science becomes computer faith. I had to be a research mathematician to be able to invent the new partial differential equations and the corresponding partial difference algorithms that I discovered. My contribution to mathematics was to discover how to execute them across a new internet. There were two things that I did with my data. First, I copied them from one processor to another processor, and I copied them via email messages. Second, I computed with them at the slow speed of 47,303 calculations per second per processor, and I did so to reach the aggregated speed that was for the first time faster than the speed of any vector processing supercomputer. Put differently, my contribution to extreme-scale computational mathematics did not reside on the processor that was not a member of an ensemble of processors. My contribution to mathematics reside on the processor that is a member of an ensemble of processors and also resides on the entire ensemble itself. Yet, my parallel processing experiment had to wait until the 1980s, when 65,536 processors became available for me to experiment with. I said that a petroleum reservoir model that runs on 3 instead of on 4 forces is akin to driving your car on 3 wheels. And with the 4th tire deflated. The lesson that I learned is that you must be a polymath, not a mathematician, to solve the multidisciplinary grand challenge problem that is beyond the frontiers of arithmetic, algebra, and calculus. The reason I could move back and forth from the blackboard to the storyboard is that I am a research mathematician and a research physicist. I knew the 4 forces that define the second law of motion of physics when applied to oil fields, and knew that law forward and backward, and knew how to encode that law into a system of 9 coupled nonlinear time-dependent and 3-dimensional partial differential equations of calculus that governs the 3-phase flows of crude oil, injected water, and natural gas that is flowing across an oil field that is a mile deep and that is the size of a town. To solve the Emeagwali equations that are my contributions to mathematics, and do so across a new internet that is a new global network of 64 binary thousand processors, demanded that I discretize the problem domain of the initial boundary value problem To discretize the problem, I approximated continuous space with discretized space or a finite grid. My new system of partial difference equations of algebra are the discrete versions of my new system of partial differential equations of calculus that I invented. As a research mathematician that is also a research physicist and that is also a research supercomputer scientist, my interdisciplinary knowledge was the necessary tool that gave me the intellectual maturity that I needed to correct the century-old critical errors that I found in calculus textbooks that were written for the petroleum industry. Those errors in calculus found their way from the classroom to the petroleum reservoir simulator used by ExxonMobil Corporation. I should mention that when I discovered that new calculus, or the Philip-Emeagwali equations, I had to create new algorithms that led to new algebra that also codified the second law of motion of physics. Inventing an equation is like making your words a part of the Holy Scripture. The Philip-Emeagwali formula was not for the blackboard alone, nor was it for the motherboard alone. The Philip-Emeagwali formula was invented for parallel processing across my 65,536 tiny computers, or as many processors, that encircled a globe in the way the internet encircled planet Earth. The Philip-Emeagwali formula made the news headlines in 1989 and was highlighted in the June 20, 1990 issue of the Wall Street Journal. 11 years later, that Philip-Emeagwali formula was reconfirmed by then US President Bill Clinton and reconfirmed in his presidential speech of August 26, 2000. The parallel supercomputer is a disruptive technology that gives tech companies some competitive advantage in their drive for market leadership. The roots of the story of how the fastest supercomputer was invented began several millennia ago and began when our ancestors had no computing aid. For millennia, our ancestors used their fingers and toes as their computing aids and had no mathematical symbols scribbled on their cave walls. For the last 100 years, the word computer was prefaced as human computer, analog computer, and electronic computer, digital computer, distributed computer, parallel computer, and supercomputer. A change in how we look at the computer was accompanied by renaming the computer. The paradigm shift in supercomputing manifested itself as a change in the name of the technology, such as changing from sequential processing that began with computing aids, such as the abacus that was invented 3,000 years ago, to the parallel supercomputer that became the world's fastest computer when I discovered it on the 4th of July 1989. Over the centuries, we changed the ways we counted. We changed from the table of logarithms to a mechanical calculator to automatic computers that used vacuum tubes. And then our computing paradigm shifted to transistors embedded in integrated circuits. On the 4th of July, 1989, I figured out how to record an increase in computing speeds and do so across a new internet that is a new global network of 64 binary thousand tightly coupled processors that were simultaneously solving the grand challenge problem that I chopped up into 64 binary thousand problems. That invention, called parallel processing, triggered a paradigm shift in how computers are designed and defined. That invention changed the way we look at the computer. The new computer changed from computing only one thing at a time to computing many things at once. In 1989, I was in the news because I figured out how the new computer can solve in one day a grand challenge problem that the old computer needed 180 years or 65,536 days to solve. It's impossible to fully describe how I felt the moment I experimentally discovered parallel processing. At a visceral and intellectual level, I felt like I was a part of human progress that was bigger than myself. My discovery of practical parallel processing felt like I caught a fish that was bigger than myself. My discovery of parallel processing was computing's equivalence of reaching the top of Mount Everest and being the first person to reach that summit. My invention is the subject of school reports because it is a contribution to the development of the computer. That invention redefined the word computer in the new definition for the 21st century. The computer is a machinery that is powered by an ensemble of up to billions upon millions of processors, with each processor akin to a tiny computer that shared nothing. I believe that our children's children could parallel process across their internet and do so to upgrade their 22nd century's internet to that century's supercomputer that should be a planetary-sized supercomputer. I invented a new internet that I theorized as the granite core of a new supercomputer. In 1989, I was in the news headlines because I figured out how to reduce 180 years of time to solution on one computer that was powered by only one processor to only 1 day of time to solution on a supercomputer that was powered by 64 binary thousand processors. My contributions to geology, mathematical physics, and supercomputing is this. I figured out how to compute faster and do so to discover and recover otherwise elusive crude oil and natural gas. Back in the 1980s, practical parallel processing was an uncharted territory of human knowledge and a new frontier without a map. The marriage of partial differential equations and massively parallel processing was pretty abstract to grasp, but amazingly powerful. In weather forecasting, solving the difficult to calculate primitive equations of meteorology tells the weather forecaster tomorrow's forecast. Back in the 1970s and 80s, to parallel process across an internet was the most complicated concept and the hardest area of computational mathematics. If you are the first person to parallel process and to solve the toughest math problems, you will be ranked as the world's smartest person. Back in the 1980s, 25,000 vector processing supercomputer scientists avoided this grand challenge problem and did so because it was ridiculously difficult to solve. The precursor to the grand challenge problem that I solved on July 4, 1989 was first posed in a science fiction story that was written on February 1, 1922. My contribution to physics was that on the 4th of July 1989, I discovered how to turn that science fiction called parallel processing that then 66-year-old Albert Einstein presumably read about in the January 11, 1946 issue of the New York Times, and how to turn that science fiction into a non-fiction that is the vital technology that makes the supercomputer super. That grand challenge problem that was at the crossroad where mathematics, physics, and supercomputing met remained unsolved for the 67 years onward of 1922. That grand challenge problem was unsolved until I solved it on the 4th of July, 1989. Parallel processing, or solving several problems at once, upended the paradigm of sequential processing in which only one problem is solved at a time. Back in 1989, I was asked, how is the new computer different from the old computer? I answered, the old sequential processing computer processed only one problem at a time. The new parallel processing computer processed 1 million problems at once. As a research supercomputer scientist that was on a decade-and-a-half-long quest for the new parallel processing supercomputer, my magical resonance occurred on my eureka moment of 8:15 in the morning of the 4th of July 1989 in Los Alamos, New Mexico, United States. That magical resonance occurred because I discovered that my new global network of 64 binary thousand processors that shared nothing between each other can be harnessed as one virtual supercomputer that is a new internet. The lesson that I learned from my discovery of that new internet was that supercomputer wizardry is the craft of looking inside that new internet to change its outside and redefine it as a new computer. To invent the Emeagwali formula that enables supercomputers to compute fastest, that then US President Bill Clinton described in his White House speech of August 26, 2000, I visualized myself as a cockroach that was crawling along 16 mutually perpendicular directions, and doing so to traverse 16 times 2 raised to power 16, or 1 binary million bidirectional paths within my new internet that I also imagined within my imaginary 16-dimensional universe. I invented the Emeagwali formula, and I did so by visualizing myself as the extreme scaled computational physicist that was living in a 16-dimensional universe. I visualized myself as the conductor of 64 binary thousand processors. I visualized myself as orchestrating the massive computations that I simultaneously executed on each of my 2 raised to power 16 or 65,536 commodity off-the-shelf processors. That was how I discovered how to harness the millions of processors within the world's fastest supercomputers and how to harness them to solve the toughest problems arising in algebra, calculus, and physics. My discovery that occurred on the 4th of July 1989 was that the fastest supercomputer in the world must and can massively parallel process grand challenge problems. That discovery made the news headlines because I recorded the fastest speed across my new internet instead of recording it within a new computer. My new internet was a new global network of commodity off-the-shelf processors. Those processors were identical to each other. Each processor operated its own operating system. Each processor had its own dedicated memory that shared nothing. The essence of my supercomputer discovery was that I achieved a magical resonance and that I broke Amdahl's law limit that limited practical parallel processing speed increase and limited it to a factor of 8. I broke Amdahl's law limit for solving grand challenge problems, and I broke that limit by a factor of 65,536 speed increase that I experimentally recorded, as well as the factor of infinity that I theorized. Since April 1967, Amdahl's law limit was perceived as the fundamental limit to the speed increase that can be recorded across any large ensemble of processors that was used to tackle the toughest problems arising in science and engineering, such as executing a century-long computer modeling to foresee otherwise unforeseeable global warming. In the 1980s, supercomputing wizardry was to make the impossible to compute possible to compute, and to do so while solving grand challenge problems and solving them by simultaneously sending and receiving 65,536 emails at once. I sent and received each email to the 16-bit long email addresses of my new internet that was a new global network of 2 raised to power 16 processors that were along one of my 16 mutually perpendicular directions in as many dimensions. My contribution to the development of the modern computer is this. I invented the Philip Emeagwali formula that then US President Bill Clinton described in his White House speech of August 26, 2000. I invented my parallel supercomputer formula to be used to solve real-world problems and used to solve them 65,536 times faster and used to solve them across a global network of 65,536 processors that were each akin to a tiny computer. My invention of parallel processing made the news headlines because I invented the technology, and I did so by sending and receiving emails and delivering those emails one binary one binary million times faster and delivering those emails across as many email wires. The parallel supercomputer was theorized as far back as February 1, 1922. But the technology was only theorized as a science fiction. For the 67 years onward of 1922, parallel processing was debated and ridiculed as a beautiful theory that lacked experimental confirmation. Practical parallel processing remained in the realm of science fiction until my experiment of July 4, 1989, that made the news headlines upgraded the theorized supercomputer to a non-fiction. I was in the news headlines because I brought that figment of the imagination called parallel processing and brought the technology from dream to reality. That parallel processing controversy was highlighted in an article in the June 14, 1976 issue of the Computer World magazine. That article scorned parallel processing and mocked the then unproven technology as a huge waste of everybody's time. The parallel supercomputer is an invention that makes the world a more knowledgeable place and a better place for human beings and for all beings. The parallel supercomputer made me a benchmark in the history of the development of the computer. Since the first programmable supercomputer was invented in 1946, each supercomputer manufactured was faithful to its primary mission, namely to solve the most extreme scale problems arising in computational physics and to increase the productivity in industries that use supercomputers and to reduce the time to solution of grand challenge climate models and to reduce the time to market of the crude oil and natural gas that were buried 1 mile deep in the Niger Delta oil fields of southeastern Nigeria. As a research mathematician, I thought in infinite dimensions. I thought in 16 and higher mathematical dimensions, and I did so to geometrically visualize the hypersurface of a hypersphere. In contrast, the non-mathematician can only see the two-dimensional surface of a three-dimensional sphere. Back in the 1980s, and in Los Alamos, New Mexico, United States, and as the first massively parallel supercomputer scientist, I had to mathematically see the 15-dimensional hypersurface that had my 2 raised to power 16 processors that tightly encircled a globe. I visualized those commodity off-the-shelf processors as evenly distributed across that hypersurface. The wizardry of that first supercomputer scientist resides in theorizing a never-before-seen internet that is a new global network of processors, and in visualizing how that new internet can be supercomputerized. That first supercomputer wizard discovered that new internet as a never-before-seen supercomputing machinery that seamlessly and cohesively communicates as a unit and computes at the fastest parallel process speed possible. Back in the 1970s, parallel processing was ridiculed as a beautiful theory that lacked an experimental confirmation. I was mocked by vector processing supercomputer scientists who believed that I was attempting to make the impossible to compute possible to compute. The main argument that was used to attack my parallel processing was this: if a global network of 65,536 processors that shared nothing was used to solve a grand challenge problem that was chopped up into 65,536 smaller problems, then the computer spaghetti code for solving each problem, as well as the primitive emails for communicating each computer code, will fall out like bolts which fastened an airplane very loosely. The skeptics of parallel processing argued that those loose bolts could not be detected until the airplane flies beyond the speed of sound. In supercomputing, the equivalence of the speed of sound is the maximum speed of the fastest vector processing supercomputer ever built. On the 4th of July 1989, in Los Alamos, New Mexico, United States, I became the first person to break that supercomputer speed record. For that contribution, the name Philip Emeagwali became a benchmark in the history of the development of the modern computer. I'm often asked to describe how I want to be remembered. I want to be remembered for my contributions to science. I did extensive video shoots because I want posterity to know what I sound and look like. 2,300 years ago, Euclid, the father of geometry, lived in Africa and in a predominantly black city. There is no record that Euclid once traveled outside Africa. Yet it is assumed that Euclid is white and of Greek ancestry, which is as odd as assuming that a historical figure in ancient Greece, such as Julius Caesar, is black and African. My photos and videos will show posterity that Philip Emeagwali is black and born in sub-Saharan Africa. What if the Igbo-born slave Olaudah Equiano, who fought against slavery, was white? Would Olaudah Equiano have entered into Nigerian school textbooks? What if William Wilberforce was a black African? Would William Wilberforce have been deleted from the Nigerian school textbooks? My discovery of practical parallel processing had been absorbed into general knowledge of the supercomputer. The impact of my contributions to the development of the computer can be measured by yardsticks such as the number of school reports on contributions to the development of the computer that mentions Philip Emeagwali. On the gravestone, you cannot distinguish between an astronomer that discovered a planet in the solar system and the one that discovered only a rock in his backyard. And by the end of this century, the 1 million active research scientists will be forgotten, just as the 1 million before them were forgotten. The reason is that only 1 in a million scientists have an afterlife as the subject of school reports. Those school reports, in turn, are what gave 16th century Galileo Galilei and 17th century Isaac Newton immortality. The school reports on Euclid, the father of geometry, that lived 2,300 years ago in Africa, are more durable than a bronze monument of Euclid. Immortality is maintained on the lips of school children. The spirit of the inventor will forever be embodied within her invention. The inventor and her invention are forever intertwined. I am in school reports, and I believe that I will be in school reports for as long as my contributions to the development of the computer and the internet remain relevant. For me, Philip Emeagwali, my discovery that occurred on the 4th of July 1989 of practical parallel processing as the invention that underpins every supercomputer has kept and will continue to keep my name in school reports. That contribution will continue to keep my name in circulation around the internet. Thank you. Thank you very much. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.